Okay, so good morning and welcome to the Machine Learning Coffee Seminar again. And I'm very proud to present you my ex-colleague, Eija Honkavaara from the Finnish Geospace and Research Institute. She's the research manager and she's going to talk about machine learning in drone research today. So please.
Thank you, Laura. Thank you for inviting me. It's very interesting to come to talk here and see people at Aalto University, and good morning to everybody. Yes, so Laura already told that I'm talking my perspectives about machine learning in drone remote sensing, and I'm leading research group in drone research at Finnish Geospatial Research Institute, and we have also Drone Finland drone research ecosystem there. There are many colleagues who are also contributed to this presentation, so thanks to them. So about our Drone Finland. So we are like research and innovation center in drone research, and we are located in Finnish Geospatial Research Institute, but we are also collaborating with many different entities, companies and institutions. We have started drone research already in 2008, and we are working with remote sensing. I will specify it more clearly soon what I mean by remote sensing. One of our major topics is new sensors and rigorous sensor data processing, because we think that it will really then give us a possibility to automate different analysis tasks. Also test fields and calibration are important. We are working with the sensor and system and data positioning and situational awareness. We are doing different mapping and analytics tasks. One of the important trends nowadays are these digital twins. Then we are aiming at this kind of real-time and autonomous operation, and 5G is one of the important facilities which makes this possible. We have a lot of application know-how, but as I mentioned already, we are collaborating with many different organizations. And we are also transferring our results to industry and society, and many of the results from our drone research is already available in some commercial applications. Here are some examples. We are working with future technologies. I will talk about something about the technologies. We are working with different environmental applications, also with a built environment, and then real-time applications like in some security-related research. I'm not talking about this lowest level here today, but I'm talking more about our environmental applications. Shortly about the content, some introduction about remote sensing and about drones in remote sensing, and then our research in this field. Then I will tell about 2 case studies in forestry and precision agriculture, and then conclusions and discussion. Okay, about remote sensing. So it means that we are acquiring information about object and phenomenon without making physical contact with the object. And especially we are working with the earth objects. And it's used in many application fields like geography, land surveying. So all maps what we are nowadays using, they are based on remote sensing. Agriculture and forestry are very important applications, and most of the earth science disciplines are also based on remote sensing. They are using data that is provided by remote sensing, and they are connecting this to different models and then making analytics. But also it's very important for different military intelligence, commercial, economic, and many application fields. And in remote sensing, we can talk about different levels of interpretation. One is mapping, so it's like classical map making. We are interpreting objects and acquiring information and so on. One is monitoring, so we are following the state of the object. And then finally, this third level is application and actuation, so that we are integrating our mapping analytics to some operational work For instance, like in agriculture, we can make some pesticide optimization based on information what we get maybe in real time from the field, that there are some insects or diseases, and then we go there and make the tasks. Different platforms, how we can use. We can have space platforms, so that is above 100 kilometers. That is also one of the very fast developing field at the moment. So there are classical satellite sensors, but there are also all kinds of CubeSats and free data coming, so it's creating a lot of new applications and business also. Then we have these classical manned aircrafts which are operating from 60 to 10 kilometers, and they are typically used at the national level mappings. Then drones, at the moment they are mostly used from 10 meters up to 150 meters, but of course that is also living, so in the future maybe also higher altitude drones are available. And then we have terrestrial applications, like here we can have remote sensing in cars or backpacks, and also industrial applications, very close range, maybe 1 meter or a few meters distances. And also drones are going indoors and caves and everywhere. So we are talking about remote sensing in many cases, and then here are these some kind of application potential. So satellites, they have a typically very low flexibility. They are getting better, but in the traditional satellites which are going fixed orbits, they are not so versatile, but they are covering very large areas. Then we have airborne aircraft sensors. They are covering quite large areas, and they are quite flexible. Like then drones, they are working in very small areas locally, but they are very flexible. And then terrestrial systems, they have even less coverage. And then when we are going to the drone topics, we can have drones in different scales. So the smallest one are like sizes are some millimeters, like insects or handheld drones. Then we can have very big military drones that can fly and operate tens of hours. And then in applications what I'm talking about today, we are having this kind of, now I'm talking about these multicopters, but the techniques are also feasible for fixed wings. So the sizes are something like 1 to 5 kilos, and they cover a few hectares areas, like 10 hectares per flight or so. In remote sensing, we always have to remember when we are developing remote sensing to some application, it's very relevant in also machine learning, that what kind of data you are working with. We are talking here about different resolutions, so we can have different spectral resolutions. So it means that we can have color sensors, thermal sensor, multispectral sensor, hyperspectral sensor. I will show some examples very soon. Our spatial resolution, it means our ground sample distance. It can go from millimeters, decimeters, and if we go to space, they are already can be 10-meter resolutions. Temporal resolutions, we can have like continuous following of the like every hour or every 10 minutes or so if necessary, and then we can go to daily or weekly or so. And then radiometric resolution tells about data quality, how small details, for instance, we can identify from the data. So, for instance, bit resolution tells about that. And then for each application, we always have to find the optimal resolutions and technologies. This is one of the important topics in our research at the FGI. So about some commercial available solutions already for drones. So here is Drone Deploy. I don't know if you know about the Drone Deploy, but it's one of the cloud services where you can install your Phantom, which is mostly used drone in the world, I guess. So you can install it with your mobile phone, and then you can get access to this drone deploy service. And then this is still quite interactive. This is from precision agriculture. So in this case, farmer is controlling the process. He selects areas of interest, tells when he wants to have data, and then he makes all the decisions. Then you have the mobile application, by which you can use the flight planning and launch access of data, which is then sent when you collect the data. It puts it to some cloud computing service, and then you can have different outputs like red color mosaics. You can have some surface models, and then based on this data, it can calculate very cross-resolution outputs, like make estimation about the vegetation health. And these costs, this kind of system are quite feasible to buy also by individual farmers even. So drone costs maybe 1,000 to 2,000 euros. Sensor can cost some 500 euros, and then this kind of service, it costs maybe 100 euros per month, and then you get the results in some hours. So this is already quite good. But of course, this is very, very simple, and it doesn't do any intelligent analytics. And a lot of things have to be done. We have to have much understanding about the environment, and we have to develop methods and models to really start using this kind of systems in an efficient way. Here is also, I showed just briefly, I hope this is working. So here is one link. We have, maybe it doesn't show, I see the link here, but you don't see it. So here is an internet link to Mosaic Mill pages. So Mosaic Mill is one of the Finnish companies who has established this kind of service. I don't know if it... Yeah. I think I'm not going to go here because... Oh, yes. Let's have a look if we get here. Yeah. So it's just... This is open for everybody, everywhere in the world. They have different levels of the data, so they really offer this kind of service where they are detecting every tree in a forest when a user sends them data. They are using some point cloud data, and then they are using spectral data, and they are calculating like detecting trees and calculating tree parameters, and this service, I think it even calculates some forest management plan for the user. Yes, okay. So these were just some examples about the current state of art, and this is already very, very advanced, and actually something what I'm telling soon, it is also using as in the background of this system. So then maybe something what interests you. So building drone-based analytics. So this is a simple procedure. What we need to do, we need to collect data. We need to do data analysis. Then we build some models, and then we analyze the models and compare it with the data. And then after we have developed the models, we can make some large-scale applications. So here are these data capture. So we need some drone data, but we also need in-situ data. There is also some weather sensor. So these are quite relevant data sets in agriculture. And here is one example from one very high-quality paper, what kind of applications in agriculture you can have. So we have the farmer again, who is making his analysis and planning, and then he gets the data from different sensors, and then the system can even run autonomously. So this kind of cyber physical management systems are being built, for instance, for agriculture. So about drone research at our institute, so we have our drone fleet. Examples of the drones are here. So we are using both very small drones, commercial drones. We have some electricians who are building our own drones to serve our specific applications. And then one of our newest drone is this Avartex hybrid boxer drone, which has big payload of 5 kilos, and it has 2 hours flight time. So like this is one of the directions that we have very long flight time, so we can build very efficient and cost-efficient solutions. This is Finnish technology. About the sensors, I'm talking now about camera-based research. So you can see here multispectral, hyperspectral, and then RGB sensors what we are using. So related to this spectral resolution, when we are working with vegetation, it's very important to know that how is the vegetation spectra. And based on this vegetation spectra, this is in from visible to near infrared range from 400 to some 900 nanometers. So there are some specific regions where you can make analysis about the quality of vegetation and so. So for that, there have been built some multispectral systems that have some specific bands in some important areas, and then this is very efficient. Then we can have the hyperspectral sensors, which are really, they are recording the entire spectra. So I think I have here some example about then. This is the multispectral spectra from one of our cameras. So it has 5 specific points where it measures, and then our hyperspectral camera records the whole spectra of the vegetation in this specific range. Of course, by RGB cameras you can also collect nice or some spectral data, and it's useful also this. So we have color cameras, we have red, green and blue spectral bands, or then we can change them to color infrared camera. So there we have also infrared bands. And from this kind of camera images, one thing what we can also collect is we can create point clouds. You will see later some other examples about point clouds, but point cloud is really like LiDAR is measuring point clouds. We can see that what is the geometric structure of the object by using this kind of point clouds, and it's also very useful in many applications. So when we are working with data, calibration is a very important thing, and this is one of the important topics what we are using at our institute or working and developing. So calibration makes us to understand, or like when we are making measurement by our camera in one place, and then if we make measurement the same camera system in another place, so if the system is calibrated, so these measurements are related to each other. And this is what we are doing with our calibration. We are using geometric calibration, so to know lens distortions. We have also multi-camera systems, so we need to calibrate these sensors all together. Then we have also the radiometric calibration, so that we can really calibrate the spectra. Here we have our 2 hyperspectral cameras which we are calibrating. We are also then in normal campaigns, we are still using some panels so that we can really accurately calibrate the spectral data so that it's comparable in different places. Some capture process, we are capturing data. We need to georeference the data so that we know where the image is and what are the fields of the images. I mentioned about this point clouds, so we make this dense image matching to create point clouds. So when we have observed some object from 2 directions, we can use stereoscopy to calculate point clouds. Then we need to do radiometric modeling. I have one example about that. And then finally, for instance, we have these point clouds, and then we have some spectral mosaics which we are fed into our machine learning processes. So I mentioned already about radiometric modeling, so it's very important. So when we are collecting data, we have very different conditions. So we can have like cloudy or varying condition. So here all the differences in between the different images, they are because of changing illumination condition. So this is one topic what we have been struggling a lot to be able to develop good machine learning tools. And then another thing is also when we are flying in sunlight, it also makes our data this kind of, it's not uniform, because when we see object from different directions in our images, so this light scattering phenomenon, bidirectional reflectance distribution, it will disturb. So all this have to be corrected, and here is a post-processing based approach, then the whole processing chain for certain analytics task then what we are doing. So we capture the data. I already told about all the georeferencing tasks, and this is for tree detection, so we make then individual tree detection, and for every individual tree we are evaluating the spectral information. Here we have hyperspectral data, and then data for this spectral analysis comes from our radiometric processing chain. And finally, when we have reference data and we connect it to these different remote sensing features, we can do different classification and estimation models or tasks. Okay. Then I have some example studies. So if you have something to ask, questions are also welcome. So here from our forestry application research, so handy, you can really collect data at different seasons efficiently, from at least from small areas. Here is one example about tree species classification, as well as forest inventory is also included here. So this was a test case in Luonnonvarakeskus test site. We had several forest plots, and idea was to make this inventory in these plots very efficiently. Currently, there are humans who are walking in the forest, and it's very laborious to collect there and measure diameters of the breast height and tree heights and species and different things. So UAVs could provide nice tool for that. This is from 2014 already, and flying height was something like 90 meters from ground level, and it was then something like 60 meters from top of the trees, and we had ground sample distances, pixel sizes. For RGB color data we had some 2 centimeters, and then hyperspectral data about 6 to 7 centimeters. So this is really accurate data, at least it was at that time, like very first time in the world when this kind of experiment was done. And then we were studying the species classification and also recently this inventory of the trees using the data, and there is also paper about this available. So here is the workflow, what we were doing. So first of all we have the point clouds, and we calculate the canopy height model. So what is the height of the canopy in the forest above the tree, and then based on this we made tree detection, and then also we get from point clouds we get different features like heights and different percentiles that where are the points. I will maybe show a little bit more about that very soon. Yes?
So this is completely offline, right?
Yes, currently this is offline.
Okay. And how much time does this take compared with the actual drone sensing?
So of course drone sensing is done in maybe 1 hour or so, and then processing, it depends what kind of computer you have, but it takes, this process what we are now doing, it takes maybe several days, or to get results first time in the world it has taken also a long time. But of course then when the companies are making the procedures very efficient, it can probably 2 days or so. It depends how much you have resources. So like we have very dense point clouds for instance, so if you have some efficient cloud server, it can be very fast. But of course we are developing, this is our objective, to make it like real time. But we have also some projects how to make it real time. Now this has been really post-processing.
Can you say how big an area was it? So if you say that it will be developed in a few hours, or how large an area was that?
So I would say that like something like 20 hectares or something like that it could be. But because it's automatic, so it depends on resources. So it's fully, because everything can be really efficiently parallelized and so on. Yes. So yeah, we had trees, and then when we have individual trees, then we take some spectral features from our hyperspectral data, and then also we are using color features from our color mosaics, and then we are using some machine learning to estimate tree species, and then to calculate the diameter of the breast height, which is, yep.
Is it mostly based on the height of the tree and location, or what other criteria can go into it?
Tree detection.
Yes, tree species.
Species, it's based mostly on spectral features in this case. Yes. Okay. And then we can also calculate different other inventory parameters like location, tree height, and crown diameter. And the process what we have been using in these studies, we have been using Python-based approach. So there are fusion-based tree detection, and then we have LAST tools to calculate different point cloud parameters, and then we are using this R statistical system, and then KIDAL and scikit-learn from Python to automate. Yep.
This machine learning box which you have there, is it done in supervised manner or unsupervised or semi-supervised?
This is supervised because we are investigating and developing the models. So yes, we need information about the object in order to make models.
Means it's like someone measured these species trees.
Yes, we have a lot of like field work. We know a lot of different tree species and their parameters. And then the idea is that after we have trained the system, then we can use it in different environments. Of course, the tree parameters, they change in different areas in Finland, so it's not so kind of you have to train your systems in different areas. Here is, I don't know how well this is seen, but we have the point cloud here, and then we can filter the ground level. There we can have the digital terrain model, and then we can calculate the canopy heights out of that. And here is this, we have been using this fusion. This seems to work very well in our northern forest. So we have this kind of spiky type of trees, so it very well detects this kind of trees. We are also using segmentation-based approach, but it's not so good. So our tree detection accuracy is in some, at best it has been something like 90% or so. It's not perfect, but it's quite good. And then, so we are really using feature-based method. Another option would be some convolutional neural networks. We are also working with that, but I don't have yet results about that. But we are really extracting a lot of features from the spectral data, like mean spectra of pixels and median spectra and normalized spectra and so on. So and then we have also different features from point clouds, like different percentiles, percentage of points whose weight are above some n% from maximum height and so on. So this is one way to do the analysis. And then we put everything here. I think probably here you can just see this is from this 2017 example, that how we were integrating different software to do the processing. So they are not at the moment this kind of system that makes it autonomously. You have to collect different bits and pieces everywhere, and then you put it together, and you can do it like this. So maybe I'm not going to details in this. Something about accuracy. So in this study we were comparing different methods. So like random forest, MLP, neural network, and different methods. So at best the accuracy was for random forest, and then this multi-layer perceptron about 95%. And we were also like, this is our research, that we then compare different materials, so we can have some hyperspectral features or just 3D features from point clouds and different combinations, and then we can see that which data set works the best. So this is like developing methods still. And then also in the best case, this is for random forest classifier, then we analyze that how well different tree species are detected and classified. So we have pine, spruce, birch, and larch in this forest. So there are like, so, and now the process that Mosaic Mill is using, it's similar. Of course, they have made their own developments and optimized all steps in that process, but here are this kind of basic feature-based approach. Here are then some examples about how the trees are detected, and then some classification results. I think that I will skip this one. Maybe some words about precision agriculture. So about background, of course, agriculture is most important industry in the world, and also the drones can help a lot to develop sustainable agricultural systems. And then it's pretty clear that in the future this AI-based farm management will be kind of standard. So we have the satellites which are collecting all the daytime data, we get free data, and then UAVs are also very important part of this system. And then in this study we were investigating silage, so that silage grass, so that the grass is collected and put to some storage and then given to cows at window, for calves at winter. So it's very important that the quality and quantity of this grass is optimal when it's collected. So we need grass quantity and quality need to be in optimal scale. So like in traditional way, it was that man went and measured the grass quality, and then there were like Valio, they had their milk car which took samples to laboratory to measure. So now we want to do it with the autonomous way. And then here is an example about grass trial site. So there were like variation in the field was created by giving different amount of nitrogen fertilization, and then it was sampled in different dates. In 4 dates in this case, it was the first cut, because grasses are cut in Finland 3 times per summer, and we had these different measurements, and here some examples from dry matter yield and digestibility. And you see here is example for first cut. So when the quantity goes up, the quality of the grass goes down, and then the optimal place is here. So there should be at least 3,000 kilograms per hectare yield, and then this digestibility value should be at some level. So this is what we are trying to find out. So we were making our drone flights there. And here are some examples about the data. So we had 4 data captures. We had our hyperspectral and multispectral and color mosaics for each date, and then this is the point clouds, which is made by structure for motion-based technologies. This can also be really like done in real time by utilizing some FPA calculation. And then we had a very similar estimation process. This is also feature-based method. So we have from drone, we have spectral data and 3D data, and we extract different features from the data. And then we had the reference data, and then we made the estimation model. So also in this study, the major question was to find that can we use this drone data to find this optimal time. And based on our results, it was possible for the first time to do it. So you can see here for different dates then when we are estimating the dry matter yield and then the quality. So when I press my button, we get always the new date data. So quality is going down and quantity is going up. So we could find this kind of correlations from our drone data. Then here are one result from our study. So we were comparing again different features. So these bars are for dry matter yield, amount of grass, and then we have the quality, digestibility value, and this shows the root mean squared error of our analysis for different feature combinations. So we got the best results when we were using, like for amount, this yield. We got best results when we used hyperspectral images, and then we had the 3D data. So then our error was 700 kilograms per hectare, and then the quality was the best. This best accuracy was obtained when we were using only hyperspectral data. So, but this was again the first time when this kind of approach has been used in forage or silage production. So it was very interesting. It's also this is for every case. You can see some examples. So this is the field where we were making the analysis. So when we are using drones, we get really for the whole field, we can see the variability inside the field. Like if it's taking the samples by a man and collecting some samples to the laboratory, then you get only one value, but there are also big variation in the field. This is just one example. In the afternoon, I will go today to Finnish Forest Center to tell about our results in related to detecting species or diseases in forest caused by bark beetles that are maybe coming also to Finnish forest and killing all the spruces, and also some fertilization need estimation. But yeah, this was just one example about new advanced topics of using drones in forestry. So I'm going into the end of the presentation. So it seems that digitalization and robotization is taking place in forestry and agriculture, and I was showing some very first generation results, and they already show that these have really great potential, like when we are using the camera-based methods, which are one can build very cheap, cost-efficient solutions. So the point clouds, what we can derive from images, they are very efficient tools for measuring geometric parameters. There are many parameters like canopy height and maybe sizes of this crop tähkä. I don't know what is in English. And then spectral data, it's needed in spectral analysis like species, diseases, pests, nutrition, and so on. And then the sensor technologies, they have really developed explosively. So every year they are coming new, faster systems, and they are like edge computing performance is being added to these systems so that you can really start working in real time. So of course, one reason why we are working post-processing is that until now there have not been any real-time solutions what we could have used in this kind of remote sensing research. Also drones and unmanned aviation is developing, so soon there are all the time flying drones everywhere. Then to make more intelligent models and to develop really these big solutions for problems, we need more comprehensive analytics, and we have to start integrating different data like weather. There are many IoT sensors. We have the farm history data, soil data, and so on. So, for instance, in agriculture, all this need to be integrated to make really this kind of physical farm management possible. And then we need data to develop our machine learning models. So I think probably we need data from different conditions for different sensors and so on, so to make this possible, all the analytics for you and us. Of course, one question is that what are the efficient machine learning technologies for different applications? I was presenting some feature-based techniques, but also these deep learning systems and so on. So these are future questions to be solved. So this is one of our objectives, to go real time. We have already in drone, we have this kind of real time capable sensors and mobile connections. So this is something what we are developing. This is my last slide. So really, I think we are coming from different disciplines, and I think it will be very advantageous if these different disciplines can be integrated. Like our systems and analytics, it has developed very much. For instance, all the structure from motion system, we had already similar system almost in photogrammetry, but then we got this structure from motion from computer vision sector. It was really made robust, and now many of the problems have been solved because of that, and I think that we can also find many other possibilities integrating knowledge from remote sensing and ICT. So I found data science Venn diagram. I don't know, maybe this is something what you are shown everywhere. Remote sensing is not mentioned anywhere. There is hacking skills and mathematics and statistics and expertise. And then here is the data science and machine learning parts. And maybe we are also one layer with our remote sensing systems here in this overlap area. I don't know. So this was my presentation. I used most of the time. So thank you. Any questions?
I had some good questions already, but I think there's still time for one or two quick ones. The last one.
Yeah, like I just was wondering, like this 95%, for example, that you showed that you can classify the species of trees. Like, is there? I mean, it's very general question, but is it sufficient requirement for like people that are monitoring the species or things like that?
Yes, I think this is already, if we can get this kind of result, it's good enough. Yeah.
Okay, enough for who. How about machine learning bias? You said that this works best for managed forest. So can you give an example? Does this work best for really managed forest? Does it work at all for unmanaged forests?
Yes, we have used it also in unmanaged forest, but it's much more difficult. So, because they are like at different levels, trees, and then they are mixing. So accuracy is not as good in unmanaged forest. But of course, one problem is to solve this managed forest problem, and then second one is this unmanaged.
Okay, so you're biasing towards managed forest.
Yes, but anyway, managed forest it's one application where it is used already. But then maybe more data is needed for unmanaged forest if you want to have good quality, and also maybe laser scanning would be better in that case. But when you know that you are going to managed forest, you can use this kind of very efficient method and cost efficient.
My question is about like the data collection. You have chosen some hives to collect the data in different conditions, and have you tried different? Would it bring more if you would collect from closer and take more, precise?
I think it is also one question. So in some applications, this is like what we have been using, it's optimal, but then, for instance, if you want to identify individual insects, for instance, on leaves, then you have to have a millimeter resolution and you have to go very close. But in this application, of course, we have been collecting already data from different heights and compared that what is the good. Yeah, but its resolution is, spatial resolution is very important parameter in these applications.
Are you certifying any of your test range with any other test ranges in the European Union or anywhere else in the world? This is primarily for global corporations that need a certified system, so the data that's captured becomes part of the legal evidence, particularly for defending the corporations against environmental lawsuits.
Yes, I think we are very open to share our data, but in this case, these are like specific case studies, so I think we have not shared it. But for instance, this summer we have been collecting with the Finnish Forest Center some data sets. So idea is that we are sharing this spectral data, for instance, so that all other organizations can also share this and develop machine learning methods using the new data. So principally yes, but of course we are. It's so much beginning.
Related to that is Mosaic Mill. Is that a Finnish government-sponsored site?
No. Mosaic Mill is private company.
Private company, it's a few guys.
Okay,
Yes.
but they're making that data public. Is that how I understand it?
No. They are not making it.
Private
So
data.
it's a business cases.
They're based in Finland.
Yes.
Okay. So, but thank you, and so thank you again, Eija.
Thank you.